This is a typical example of an electric circuit. I'll just tell you the components, then I'll explain series and parallel connection very quickly. And then we'll stop for here today, and then we can go for the next class. Right? So this is a symbol for the ammeter. Ammeter is used for measuring current. Ammeter is used for measuring the electric current. Then this is symbol for voltmeter. Voltmeter is used for measuring the potential difference. That's terminal PD. Potential difference was across this end, from here to here, from this point to this point. That's what this voltmeter is measuring. And then this is what? This is a light bulb. A symbol for a light bulb. This is one of the symbols. There are other symbols. There's another symbol for light bulb. Then this is what now? This is resistor. The fixed resistor. This is a resistor. This is also what my resistor. We call this one R1 and what? R2. Right? Later on, you come to see that these resistors are connected in what? A series. Resistors. And then these are what now? This is cell. And this is a battery. What is the difference? A cell is plural. If I have one solar power, this is an electrochemical cell. It's what is powering the whole system. If I have only one, it's a cell. If I have more than one, it's a battery. Like this one here, and I have two of them. That's why I just separated them for you to see. Then it's possible that I can have, that circuit I just showed you now is closed. Let me go back again. This circuit is closed. It's closed. I want to show you an open circuit. If I have this, let's say I have something like this. This is a switch now. This is a switch or the key. Switch or key. In this case now, the circuit is what now? It's open, it's broken. If I want to complete it, I close the switch. Now, if I want to have resistors in series, I'm talking about series and parallel arrangement very quickly. Series arrangement. If I have this resistor, another resistor, another resistor, like this. This is R1, this is R2, this is R3. Because the same current is flowing through them, we say they are what now? They are in series. The same current that passes through R1, passes through R2, and passes through R3. The same thing will happen for what? For this guy. So I have three cells here, which is the battery. So let me call this one E1, E2, and then E3. That is the electric force, right? This one is also what now? A series connection for the cells. And if I want to find the value, the equivalent resistance here is going to be a big R. That's one single value that represents all of them. If I have values in series, I want to find the equivalent resistance. I will have what now? To add them up. R1, R2 plus what now? R3. The same thing for what now? For the cells. If I want to find their equivalent EMF, it's going to be what? E1 plus what? E2 plus E3. However, it becomes different when I have parallel connection. I'll show you what parallel connection looks like now. If I have to connect them in parallel, this is what they look like. I'll have the resistor, this other resistor, and this other resistor. You're making noise with that door, please. So I have this. This is R1, R2, and R3. In this case, now you realize that what now? They can have the same potential difference. They will have the same potential difference. They have the same potential difference, but the current that is passing through them is different. The current I here will split into three: I1, I2, and I3. It's split into three. So the same different current, but their potential difference is different. So for parallel connection, the PD is the same. It's the same. And if I want to find the equivalent resistance, R, I'll use the reciprocal in this case. Right? I'll have 1 over R, which is the equivalent resistance, 1 over R1 plus 1 over R2 plus 1 over R3. That's how I can get what now? The equivalent. The single value that can represent all of them. Alright? Then if I want to do for cells, let's say I want to do the same arrangement for cells, right? If I want to do that for cells, I'll have the first cell, the second cell, the third cell. The same parallel what? Arrangement. One of the things I didn't explain to us earlier on is that this longer part of the cell is the positive side, and the shorter part is what? Is the negative side. Take note of that. The long part is the positive side, the short part is the negative side. So in this case, I also have what now? A parallel what? Arrangement for the cells. Because different currents here, and different currents here. But in this case, if this is E1, and this is E2, and this is E3, the equivalent EMF would be that of any one of them. Could be E1, could be E2, could be what now? E3, any one of them. So you see that, please take note of that. It's not like you do reciprocal for the cell. For the resistors, we need reciprocal value, and then for what now? For the cell, just one. So what is the advantage of the parallel connection for cells over the series connection? It's important to note that if you want stability, parallel connection is better off. But if you want large amount of what now? Of energy supply, the series connection is better off. If you want a large EMF, series connection is better off. So I'm going to hold on here. Maybe in next class I'll go further and then we'll do some calculations all together. Is that right?